Chapter D, we're going to look at here temperature, pressure, and altitude. And the definition of the lapse rate is you take minus the derivative of the temperature function as a function of altitude. You take it with respect to the altitude, dc. And we're going to be looking at a theoretical derivation of this for an adiabatic rise in the atmosphere. But for now, just take that as definition, that as you go up from the ground, z, the temperature changes. The temperature drops. So we put a minus sign in front so that we get a plus value. So if we have something, for example, of 6 degrees Celsius per kilometer, that means when you go up a kilometer, you drop 6 degrees Celsius. And that's called the lapse rate. Now, in the lower part of the atmosphere, you have a lapse rate. So we're looking at that later. So we need that formula, and that formula for the lapse rate is our equation 10. Now we'd like to do hydrostatic equilibrium. This is another very important relation. And here we go to Pascal's law. Pascal's law. So let's consider a column, a rectangular column of fluid. It can be water, but it can also be the atmosphere. And we're going to look at here what the effect is if we're down underneath it, if it's above us. So here is a rectangular column of fluid. And there'll be a force on us down here. So there's an area down at the bottom. And let's measure the distance from the top. This is the depth. And we're going to be down here at the bottom. This is Pascal's law. What is the pressure down at the bottom? Well, the force down at the bottom is going to be the weight. So the weight is the mass of, it'll say water, times g. And the mass of the water is going to be the density times the volume. And the pressure at the bottom is the force per unit area. So if we put this together, we'll have rho times the volume times the g. And that's over A. But the volume is equal to the area times the depth. Now you see the areas cancel out, and for the pressure, you get rho g x. Now that's Pascal's law. Now when you have a lake and you're underneath the water, this is the pressure that's going to be down at that depth if there were no atmosphere. But since the atmosphere pushes on the top, you'd have to modify this and add the atmospheric pressure. But if we apply this to the atmosphere, this is the atmosphere. So we would just leave it like that, because if you go higher and higher, then you basically have nothing pushing down at the top. You have outer space. But what we're interested in here is measuring from the ground. So let's say the ground is down here, and this is some z above the ground. That's the elevation. Then we can write down x plus z is equal to some constant, where if we then go lower and lower, the x increases, but the z decreases, and vice versa. So the differential dx plus dz is equal to 0. So we get that dz equals minus dx. So if we want to look at a little dx and dz, so let's look here at the little, this is the little, say this is a dx. This dx is going to be equal to a minus dz. That's the relationship. And this is, say, the area. And this here, we can think of this as having a little pressure differential, dP, is equal to rho g dx by just taking the differential here. dP is rho g dx. And then you look at the relationship with the minus sign, so that means the pressure, dP, is minus rho g dz. So coming from here, we can write the derivative, the pressure dz is equal to minus rho g. And that is our equation 11 in our course.